cross-cranial parasite back in 1905. And he was the first person to ever be recorded to culture cells in a dish. And so you can see on the screen, he has these dish. It's a small petri dish, and has some pipettes, a little bit of liquid, and has some cells inside of them. So this is us today, though. So really, in the past century, not much has changed in the way that we're doing biology as well as culturing cells. This is a problem because, in general, cells in 2D are not going to be mixed with our actual physiology and what occurs in the body. And that's really because the body, the human body, is a 3D structure. Cells exist in 3D space. And so this is a self-force map done by Chris Chen, kind of showing that cells understand the forces that are around them, the cells that are beside them, and the substrates that they're in as well. What that means then is that designing tissues, especially designing living tissues, requires 3D complexity. And so then that's what we've been trying to do as a company. So 3D bioprinting is one of the technologies, it's not the only one of the technologies that is being used around the world to try and design and structure 3D tissues. And we envision moving forward that it's really important to not only shift the entire biology world, tissue engineering world from 2D world to 3D world to create an entire ecosystem that allows you not only to design your tissues, but to analyze them as well, and to culture them as well. So, designing a tissue, you don't not only end, strictly speaking, when you create it, but you also have to, culture it and kind of mature it, depending on what type of tissue it is. So we've created this platform, which has come from a host of customers, but nonetheless, we're really trying as a company to tailor an end-to-end experience of designing tissues. So it really begins in the software. You say, hey, I want to place myself here, and I want to place this cell here. And then it goes on to the hardware, which is, hey, I have to interact with this robot that's going to understand where precisely to place things. And then at the end, it finishes off with the materials and the inks that you're going to be using. Certain inks work with certain cell types. And so today I wanted to, so then we have this platform, and we sold our platform to over 100 researchers around the world. It's a question you believe me. We have all these customers, and then I wanted to aggregate kind of what these customers or users have been doing, and really present to you a bit of the state of the art of what different bioprinting techniques. And so a lot of people have been really excited to try to figure out, how can we precisely print and place cells? And people have done that through mixing them with gels. And those gels, though, we call them ECM-based gels, because you can actually stick cells inside of them. So, we are all composed of two things, which is extracellular matrix, which is almost like a scaffold, and then the cells that go on top. And so the ECM-based materials are kind of allowing users to mix cells and then place them in certain spots. And so you can see on the top left, you can pattern the cell in a line and have them live. And that's actually a lot of the state of the art. Like, people get super excited just to be able to print the cells and have them live. And so oh my gosh. But that's kind of what we call the ECM-based gels, and it's really being used to print soft tissues. And so, there's hard tissue engineering and soft tissue engineering. When it comes to soft tissue engineering, it's things like heart, liver, brain, kidney, and so then that's kind of ECM-based gels are really leading the way for soft tissue engineering. One of the biggest challenges within tissue engineering today is that actually we don't know how to create blood vessels into we all have blood vessels. We have a blood vessel. Every cell in your body has a blood vessel at least 3 microns away to be able to give that cell nutrients as well as remove waste. And so we can only really make small structures today in tissue engineering because we don't know how to integrate blood vessels. So one of the techniques that people have been using, though, is to add in these sacrificial lattices. And so what you can kind of imagine is that you make a gel. So you make a gel, and when you're making the gel, though, you print these lines here. And these lines, what you do is that once the gel is done, you can sacrifice them, and that's what I call sacrificial. And so what it allows you to do in this slab of gel here, there's no, this kind of forced cell map is where cells are living. So the cells in the center don't live. But when you have these sacrificial molds, the cells in the center live. And so people get really excited. All of a sudden we have the screen here. People get really excited. Hey, we can start thinking and imagining about how we can make cells and tissues that are larger than centimeter large. So when it comes to hard tissue engineering, things like cartilage and bone, people are integrating in plastics along with living cells to make more rigid structures. Kind of the dream and the imagination is that you can take kind of a structure that has cells, implant it in somewhere, then that rigid structure that's plastic dissolves away, and then the cells overtake the entire structure. And so people have been doing this with bioprinting as well. And so what they do is they print out, this is probably the best picture here, they print out a thermoplastic. And so then that goes back, with one of the extruders. And then in between, they put in cells. So they'll put in cells with the ECM-based structure of either cartilage cells or bone cells. And then the idea there is that you can then take this, mature it, implant it, the thermoplastic will degrade away, and then you're left with the kind of cells maturing and growing and releasing their own scaffold at the end of the day. The last thing I wanted to present to you is this idea of gel-in-gel printing. So one of the hardest things in bioprinting is printing, especially with the technology that we use, which is deposit-based printing, is creating overhangs. And so in normal plastic 3D printing, as you can see here in a lot of the booths, people use support-based structures. And the support really helps maintain kind of the overhang as you're printing it. But in bioprinting, gels don't really allow you to do that. There's no really support gel-based structure. So what Carnegie Mellon did, actually, by a professor named Adam Feinberg, is that he decided that he would make this slushy bath. And so he would take his needle, and then he would print his gels inside the slushy bath, allowing him to make different structures. When he was done with the structures, he would increase the temperature to 37 degrees, and then the slushy bath becomes water, allowing him to pull out the structure. And so this allows you, though, you have the unlimited design freedom, really. All of a sudden, you're not limited to the constraint of having an overhang. You can create complex vascularity, in this case, which has different ups and downs and different amounts. And so we've worked very hard to make this very easy to do. And we've been actually able to replicate it ourselves. And you can see here on the left, this is it's just this hollow structure, but it has kind of the inside of it kind of tree structure, as well as nonetheless it's hollow. So doing that with just a normal FDM kind of strategy is not really possible. And on the same token here, we have kind of this branched vascular vessel tree that we created, which is also very difficult in some sense to do without any support or overhang. So these are just some of the strategies that people are using today to try to even understand more really about what is going on. As the field moves forward, not just about placing the cells in their certain orientations and having them live, which we're getting better at as a whole, as a field to do, but further say, okay, not only did I print the cells that I wanted to in the places that I wanted to, but that at the end of the day, they're actually doing what I want them to, which is if you're a heart cell, you're going to beat together. If you're a kidney cell, you're actually working together with the other kidney cells to purify something. So that's kind of the idea of having this question. Thank you.
Thank you for the amazing presentation. We have time for a few questions. Any person? Then I have a question. So you said that you have over 100 customers around the world. These are research-based institutions, but what are the prospects to take this technology to, for instance, clinical practice?
Sure. So I would say about 80% of them are universities, and then 20% are the research departments of our companies, small and large companies. And this technology, I think, when is it going to be useful is usually a huge question. And I think just like Judith presented, probably the first immediate place is for pharmaceutical testing. I think the technology has to become much easier to use. I think pharmaceutical companies don't want to hassle with all the complexity that there is right now. Graduate students will hassle with it. So you have to learn how to use the software with it, and what materials will wear. The cells have to be very the cells have to be handled in a certain way. And pharmaceutical companies just want to, plug in a cartridge, press play, and it spits out a bunch of tissues. And so, I think that will be the first application. But it's going to be very important to show that, that the bioprinter and the bioprinting technology is the only one that can achieve that structure. Because if not, everything else is usually cheaper. So if you can create it with a mold, but probably with a mold. For the clinical applications, the first ones will be very simple. It won't have any cells, it won't have any growth factors. They'll just be like a single material. But the biggest challenge is going to be the getting GMP or passing over all the regulations. No one I think today is really a bioprinter that has kind of all the regulations gone through. And it being very simple.